business. And so let me just do quick localization of primary ideals. Okay, so let me just prove this theorem. Okay, so let A be a ring. Okay, and if Q is an ideal in A, is P primary for some prime ideal P. So that's then and so let's say let S in A be multiplicatively closed. Be multiplicatively closed. Okay, then S inverse of Q is S inverse of P primary in S inverse of A. Okay, so let's try and prove this theorem. So this is saying that okay, so this is important when you want to like start doing global geometry, right? So one of the things that you want to do is you have rings, and then you have you have a bunch of rings glued together to build a scheme, right? And so like the best example that I can give you is like P1. Okay, so P1. So this is a scheme, right? Over, let's say, a field K, right? This is two pieces. This is Kx union spec of Ky. But there's some gluing here. The rings, so K, X, Y, X comma Y. So these are glued along spec K of XY, XY minus 1. Okay, and so let me point something out here. So spec of so the idea is that here K of XY, XY minus 1. So this is really isomorphic to spec of Kx. And then let's invert at 1 over x. Oh, sorry, let's localize at x. So this is K of x, 1 over x. Okay, so this is really, this y here, this thing here, is really spec of K 1 over x. And this ring here is the intersection of the two pieces. So it's like you have, you kind of have two charts, right? So you have two parts, right? There's one part here, which is where you delete infinity. This is the part where you delete 0. So this is P1, and this is spec of, so this is the point infinity, I say. So this is spec of Kx, and this is the point 0, and this is spec of K 1 over x. Okay, so this thing here is glued from two pieces. It's glued from this piece, and it's glued from this piece. And together they make this P1, which is this thing that we built from kind of Frankensteining two rings together. Okay? And this is, you know, this does correspond to the P1 that we talked about in algebraic topology. Okay? What this theorem does, this theorem here, it tells us that no matter how we Frankenstein our scheme together, how we glue it together, right, there's going to be well-defined primary decomposition of a scheme. And that's why this localization thing is important. Okay? It allows you to glue, you know, talk about primary decompositions or decompositions of schemes into irreducible components. Okay, so so the proof of this, let me see if I can do a proof in 2 minutes. The proof is not so bad. So we need to show that the kernel of A mod S inverse Q. Let's say S inverse A to S inverse Q to S inverse A to mod S inverse P is nilpotent. Okay, so what do we have? So this means that S inverse. So I think what we do something like this. So S inverse A mod S inverse Q. This thing is isomorphic to S inverse of A mod Q. This thing here, S inverse A mod S inverse P. So we use the behavior localization here. This is S inverse of A mod P. Okay, so we have this. And then we have here, so we have A mod Q going into here. And then we have A mod P going into here. And we know that the kernel of this thing is nilpotent. So this thing we know of this is nilpotent. Okay. So
what do you mean by nilpotent? The kernel is an ideal, right?
Yeah, the kernel is an ideal. What I mean is that every element in there, some power out of it is 0.
Okay.
Okay. So I ran out of time, but this means that so if y is in the kernel, then y to the m is equal to 0 for some m. Okay, so I'll do this at the beginning of class next time, and then and then we'll go from there. All right, I'm gonna stick around for questions if you guys have any. Thanks for hanging out.
What
I was saying was that I looked at the homeworks and so there's kind of 2 comments. I would start with the T. McDonald homeworks for the primary decompositions first, since those are a little bit easier. And then you have to do a couple problems. I think for like problem 36 in the dumb and foot, you have to do the 2 problems before, but they're not bad. Or you can assume them. And that's about how those 2 problems are about how primary decompositions behave under surjective ring homomorphisms. So essentially says like the inverse image of a primary decomposition is a primary decomposition, and the image of a primary decomposition is a primary decomposition. Other than that, I think the hard part is dealing with embedded primes, and I'm not going to say anything more about that, but maybe I'll make some remarks in future class. Do you guys have any questions? So the other comment I guess I should make is that you really haven't gotten so much practice with Nakayama, and Nakayama is so it'll start to come up more once we start doing tensor products and stuff. So a lot of the exercises have to do with localizing things and then using, that certain properties of maps of modules are stock local. And so that'll start to appear again. So we've you haven't really had so much of that, so that's going to come back again. So you had like a little bit of a, I don't want to say break, but a little bit of a pause as to how much homework you could do. Okay, so that being said, I'm just going to continue and try and wrap up the primary decomposition stuff. Okay, so last time, where were we? So last time we were talking about localization, and then I'm gonna do the bit about so then I'm gonna do the bit about existence. Okay, so let's just do this first. So this is kind of a loose end. Again, this is the reason why we care about localizing primary ideals, is so that you need this to do scheme theory, right? So if you want to do like a global geometry, then you want to patch rings together. then what you're going to need to do is you're going to need to have some sort of primary decomposition that behaves well with respect to localization. Okay. And so the theorem was the following. Theorem or lemma was, okay, so let A be a ring. Let S subset of A be a multiplicatively closed set. We're going to let Q be an ideal and A be P primary. So that implies that P is a prime ideal. Okay, then and then we're going to say that if S intersects Q is empty, then S inverse of Q, which is an ideal of S inverse of A, the localization of A at S, is S inverse of P primary. All right, so that's what we want to prove. All right, so so I'm going to use the property that we proved about localization a long time ago, which was that exact sequences. This isn't the only way to do this, but I'm going to use two properties. Okay, one is that localization of exact sequences are exact sequences. Okay, localizations of sequences of modules. And then the second thing that I'm going to use is the way that localization behaves with respect to quotients, which is really that same thing, right? So it says that if you the quotient, the localization of a quotient is the quotient of the localizations. And I'm going to write this down, and so you'll see what I mean in a second. So the proof. Okay, so here's the proof. Sorry, something on the screen here. Okay, so let's do this. So consider the exact sequence. Okay, so we're going to have 0 goes into P mod Q, goes into A mod Q, goes into A mod P. Okay, this is F. We'll call this F. Okay, so so by definition, the kernel of F, which is P mod Q, is a nilpotent. Okay, so this is one of the definitions of being P primary. Being P primary. It's that this thing is a nilpotent in thickening, that the map F is a nilpotent thickening. Okay, so this is what we're going to have to do is I want to show that okay, so what we want to show is that after we localize this, that it's also a nilpotent thickening. Okay, so now what we'll do is we're going to apply, so by exactness of the localization functor, so a functor is exact if it preserves exact sequences. Okay, and we saw that localization preserves exact sequences. All right, so this is S inverse of A mod Q. And we have S inverse of A mod P. Okay, so this is a localization of a, so we have this. So this one here, the one on the far right, this is a localization of a domain, right? So that's a domain. And our goal is to show that this thing, so we want to show that this thing, well, let me show you actually. So let me just simplify. It's going to have to do with that, but let me just do something. So localization is an exact functor, but we also have that this thing here, this one here, this is isomorphic to S inverse of A mod S inverse of Q. Okay, so that was one thing that we were allowed to do with localizations, right? Was we were allowed to commute localization with quotients. And same thing here.
Can I ask, was this a specific S, or is that just like a type where you just omit the identity and then make everything else invertible?
It's any multiplicatively closed subset of A.
Okay, right. I think you wrote that earlier. Thanks.
Yeah. Any multiplicatively closed subset of A. Okay, so we have this, and so again, this is this thing follows from the fact that localization. So maybe I can write an arrow to both of these. So this equality and this equality follow from the fact that localization commutes with quotients. I mean, it's really the same thing. And the proof that localization commutes with quotients is really just a reincarnation, or is just another incarnation of that localization preserves exact sequences. Okay. So, all right. So, but this thing here, right? So we want to show that now we're in the position where I wanted to say this. So in order to prove, that S inverse of Q is S inverse of P primary, we need to show that this map S inverse of A mod S inverse of Q to S inverse of A mod S inverse of P is a nilpotent thickening. Or nilpotent infinitesimal thickening. What did I call it? Infinitesimal thickening? Thickening. Okay, so in particular, we need to show the kernel of this is nilpotent. Okay? But the kernel of this map, we know what the kernel of this map is. The kernel of this map is, well, it looks like this. S inverse is the localization of a nilpotent thing. So it's the set of P bar over S for P bar in P mod Q. Okay, and so this means that so we know that since for every P bar in P mod Q, there exists some n such that, well, P bar to the n is equal to 0. We have that here, that P bar over S to the n is equal to 0 as well for every S. And hence, the kernel is nilpotent. Okay, and so this proves that S inverse Q is S inverse of P primary. It proves that it's primary. But I guess we could check one thing. If we want to go a little bit further, we can check a little bit more, right? So one thing that we could do is we could check that it's actually so. I mean, this is enough. Okay, but to be extra safe, let's check that the radical of S inverse of Q is S inverse of P. Okay, so how do we do this? So to do this, so we will use that a certain bijection that the ideals, so the ideals of S inverse of A above where I contains S inverse of Q. So this is in bijection with the ideals of S inverse A mod S inverse of Q. Okay, so this is the so-called lattice isomorphism theorem. So this bijection here. Oh. Okay, let me say how to use this for a second. So this is kind of like a little bonus thing here. Okay, and so let's just do the radical computation. So the radical of S inverse of Q. So this is the set of X in S inverse of A, such that X to the N is in S inverse of Q, or some Q, some N greater than or equal to 1. Okay, so this, by the bijection, okay, so by the previous bijection, so this is the little red thing here. So this is the same thing as the no radical of S inverse of A mod S inverse of Q. Okay, this line above, this is equal to S inverse P over Q. Okay, so let me just say a little bit about this. So why is the no radical of this equal to this? So clearly, everything in here, so everything in here is clearly nilpotent, right? By what we did before. Okay, but also the nilpotents, they're all contained in here, right? Why are all the nilpotents contained in here? Well, the quotient is a domain. By is a domain. Okay, why is it a domain? Well, let's go back here. This is the localization of a domain. The localization of a domain is always a domain, right? And so that shows that this is a domain, and so you can't have any nilpotents left over. So that's what I was doing here. Okay, and so now using this bijection again, this is S inverse of P. Mind you that this is isomorphic to S inverse of P mod S inverse of Q. So I guess I'm using this bijection and this bijection. So this proves that the radical, this proves that the radical of S inverse of Q is equal to S inverse of P. Okay? So that's what we have here. Any questions on that? So that was this loose end that we wanted to show that primary ideals localize. And so, like I was saying, there's this other exercise in the homework to do one of the last dumb it and foot exercise that's on there that allows you. So it gives you a nice trick for showing that. So the exercises before the exercises, kind of like there's a couple exercises that you need to do the exercise. They're not bad, and it just says that the local that the inverse image of a primary ideal is primary, and the image of a primary ideal is primary under certain conditions. And yeah, so this is what's going to let us, and again, this lemma here is what's going to allow us to glue things together once you start doing scheme theory. All right.